What if I told you there's a mathematical function that can perfectly clone itself? A function so special that when you take its derivative, you get exactly the same function back? Meet e to the x, the exponential function. Its derivative is incredibly special. It equals itself. The derivative of e to the x is simply e to the x. But what does this actually mean? Think about it. The rate of change of e to the x at any point is exactly equal to the value of the function at that same point. This is completely unique in mathematics. To understand how remarkable this is, consider other functions. The derivative of x squared is 2x, completely different. The derivative of sine x is cosine x, also different. But e to the x, it stays exactly the same. This unique property makes e to the x incredibly powerful in the real world. It appears everywhere, from modeling population growth and radioactive decay, to calculating compound interest in finance, to training artificial intelligence systems. Understanding this derivative is your key to unlocking these applications. In the next sections, we'll prove why the derivative of e to the x equals e to the x using multiple methods, and then see this amazing function in action through real-world examples. Get ready to discover one of mathematics' most beautiful relationships. The exponential function e to the x is one of the most important functions in all of mathematics. But what exactly is e to the x, and why should you care about it? First, let's break this down. The letter e represents Euler's number, a special mathematical constant approximately equal to 2.71828. This number appears naturally in many mathematical contexts. So e to the x means we're raising this special number e to the power of x. When x equals 1, we get e. When x equals 2, we get e squared, which is about 7.39. The function grows exponentially as x increases. Now let's visualize what this function looks like. The graph of e to the x starts close to 0 for negative x values, passes through the point 0, 1, and then grows rapidly for positive x values. Here's the beautiful exponential curve. Notice how it approaches 0 as x becomes more negative, but never actually touches the x-axis. For positive x, it grows faster and faster. This is exponential growth in action. But why is e to the x so special? Here's the remarkable property that makes it unique. The derivative of e to the x is exactly e to the x itself. No other exponential function has this property. This unique property makes e to the x incredibly useful in calculus and appears everywhere in the real world. It models population growth, radioactive decay, compound interest, and even the spread of diseases. In the next sections, we'll prove why the derivative of e to the x equals itself, and then see this powerful function in action through real-world examples. Understanding e to the x is your key to mastering exponential calculus. Now we'll prove that the derivative of e to the x equals e to the x using the fundamental limit definition of a derivative. This rigorous approach will show us exactly why this remarkable property holds true. We start with the limit definition of a derivative. For any function f of x, the derivative is defined as the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Now we apply this definition specifically to our function e to the x. We substitute f of x equals e to the x into our limit definition. Here's where the magic happens. We can rewrite e to the x plus h as e to the x times e to the h using the exponential property. This allows us to factor out e to the x from the numerator. We can factor e to the x out of both terms in the numerator, which gives us e to the x times the quantity e to the h minus 1, all divided by h. Since e to the x doesn't depend on h, we can pull it outside the limit. This separates our expression into e to the x times the limit of e to the h minus 1 over h as h approaches 0. Now we need to evaluate this special limit. The limit of e to the h minus 1 over h as h approaches 0 is a fundamental limit in calculus that equals exactly 1. Substituting this result back into our expression, we get e to the x times 1, which simply equals e to the x. Therefore, we have proven that the derivative of e to the x is e to the x itself. This completes our rigorous proof using the limit definition. We've shown that e to the x is the unique function that equals its own derivative, a truly remarkable mathematical property that makes exponential functions so important in calculus and beyond. Now we'll explore a second method to find the derivative of e to the x using logarithmic differentiation. This elegant technique transforms our exponential function into a simpler form that's easier to differentiate. Step 1. We begin by setting y equal to e to the x. This substitution will help us work with the exponential function more easily. Step 2. We take the natural logarithm of both sides of our equation. This is the key insight of logarithmic differentiation. We use the logarithm to simplify the exponential. Since the natural logarithm and e to the x are inverse functions, ln of e to the x simplifies to just x. This gives us the much simpler equation, ln of y equals x. Step 3. Now we differentiate both sides of our equation with respect to x. This is where we apply the chain rule to the left side and the power rule to the right side. On the left side, we use the chain rule. The derivative of ln of y with respect to x is 1 over y times dy dx. On the right side, the derivative of x with respect to x is simply 1. Step 4. To solve for dy dx, we multiply both sides of our equation by y. This gives us dy dx equals y. Now we substitute back. Since we originally set y equal to e to the x, we have dy dx equals e to the x. This confirms our result. The derivative of e to the x is e to the x. Logarithmic differentiation provides an elegant alternative to the limit definition. By taking the natural logarithm first, we transformed the exponential function into a linear equation that was much easier to differentiate. Both methods confirm the remarkable property that e to the x is its own derivative. What happens when we need to find the derivative of e raised to a more complex function, like e to the 2x or e to the negative x squared? The chain rule transforms these challenging problems into manageable steps. When we have a composite exponential function e to the f of x, we apply the chain rule. The derivative equals e to the f of x times the derivative of the inner function f prime of x. Let's start with our first example. Find the derivative of e to the 2x. Here our outer function is e to the u, and our inner function f of x equals 2x. We identify that f of x equals 2x, so f prime of x equals 2. Now we apply our chain rule formula. Applying the chain rule, we get e to the 2x times 2, which simplifies to 2 times e to the 2x. For our second example, let's find the derivative of e to the negative x squared. This involves a polynomial inner function. Here, f of x equals negative x squared, so f prime of x equals negative 2x using the power rule. Applying the chain rule gives us e to the negative x squared times negative 2x, which we can write as negative 2x times e to the negative x squared. For our final and most challenging example, let's find the derivative of e to the sine of x. This combines exponential and trigonometric functions. Now f of x equals sine of x, and we know that the derivative of sine x is cosine x. Using the chain rule, we get e to the sine of x times cosine of x. This is our final answer. Remember, the key to success with composite exponential functions is identifying the inner function, finding its derivative, and then multiplying by the original exponential expression. This pattern works for any function inside the exponent. Now we'll see how the derivative of e to the x appears in real-world population growth models. This is one of the most important applications of exponential functions in biology and epidemiology. The population growth model uses the formula P of t equals P naught times e to the RT. Here, P of t represents the population at time t, P naught is the initial population, R is the growth rate, and t is time. To understand how population changes over time, we need to find the derivative of this function. This will tell us the rate of population growth at any given moment. Step 1. We write out the derivative of p with respect to t. Since p naught is a constant, we can factor it out. Step 2. We factor out the constant p naught. Now we need to find the derivative of e to the RT using the chain rule. Step 3. Using the chain rule, the derivative of e to the RT is e to the RT times the derivative of RT, which is r. Step 4. We rearrange to get r times p naught times e to the RT. Here's the key insight. P prime of t equals r times p of t. This means the rate of population growth is directly proportional to the current population size. Now let's work through a concrete example to see how this works with real numbers. Consider a population that starts with 1,000 people and grows at 5% per year. We want to find both the population and the growth rate after 10 years. After 10 years, the population is 1,000 times e to the 0.5, which equals approximately 160.49 people. The growth rate at year 10 is 0.05 times the current population, which gives us about 82.5 people per year. Notice how the growth rate increases as the population grows. This exponential growth model was crucial during the COVID-19 pandemic for understanding how quickly the virus could spread through populations. The key insight is that when growth rate is proportional to current population size, we get exponential growth. This principle applies to populations, infections, investments, and many other real-world phenomena. Now we'll see how the derivative of e to the x applies to one of the most important concepts in finance: continuous compound interest. This is how your money grows when interest is compounded continuously rather than monthly or yearly. The continuous compound interest formula is A of t equals p times e to the rt. Here, A of t represents the amount of money after time t, p is your principal or starting amount, r is the annual interest rate as a decimal, and t is time in years. To find how fast the money is growing, we take the derivative of a with respect to time. Starting with our formula A of t equals p e to the rt. We differentiate both sides with respect to t. The derivative of A of t is A prime of t, and on the right side we have the derivative of p times e to the rt. Since p is a constant, we can factor it out. This gives us p times the derivative of e to the rt. Using the chain rule, the derivative of e to the rt is e to the rt times the derivative of rt, which is just r. Rearranging the terms, we get A prime of t equals r times p times e to the rt. This is our key result. Notice something amazing. Since p times e to the rt equals a of t, we can write this as A prime of t equals r times a of t. This means the growth rate is always proportional to the current amount. Example 1. You invest $1,000 at 5% continuous compound interest. What is the growth rate of your investment after exactly 2 years? First, we find the amount after 2 years using our formula. A of 2 equals 1,000 times e to the 0.1, which equals about $1,105.20. Now we use our derivative formula. A prime of 2 equals 0.05 times A of 2, which is 0.05 times 1,105.2, giving us $55.26 per year. This means at the 2-year mark, your investment is growing at a rate of about $55.26 per year. Example 2. You invest $5,000 at 3.5% continuous compound interest. Find both the amount and the growth rate after 10 years. After 10 years, the amount is 5,000 times e to the 0.35, which equals about $7,095.50. The growth rate is 0.035 times 7,095, which gives us $248.34 per year. Notice how the growth rate is much higher because the account balance is larger. Example 3. This is a real retirement planning scenario. You start with $25,000 in a retirement account, earning 7% annually with continuous compounding. How fast is your money growing after 30 years? After 30 years, your $25,000 investment has grown to over $204,000. That's more than 8 times your original investment. The growth rate at this point is 0.07 times 204,150, which equals over $14,000 per year. Your money is growing by almost $14,300 every single year at the 30-year mark. This demonstrates the incredible power of exponential growth and continuous compounding. The longer you wait, the faster your money grows, because the growth rate is always proportional to your current balance. We've covered a lot of ground in understanding the derivative of e to the x. The most remarkable property we discovered is that the derivative of e to the x equals itself, a truly unique characteristic in mathematics. We explored 3 powerful methods to derive this result. First, the limit definition showed us the fundamental approach using the definition of a derivative. Second, logarithmic differentiation provided an elegant algebraic pathway. Third, we learned how to apply the chain rule to more complex exponential functions. We also saw how this derivative appears in real-world scenarios. Population growth models use exponential functions, where the growth rate is proportional to the current population. In finance, continuous compound interest demonstrates how money grows exponentially over time. With these tools and examples, you now have the confidence to tackle any problem involving the derivative of e to the x. Whether it's a simple derivative or a complex chain rule application, you understand both the mechanics and the meaning behind this fundamental calculus concept. If this video helped you understand the derivative of e to the x, please give it a thumbs up. It really helps other students find this content. Subscribe to our channel for more calculus tutorials, and don't forget to hit the notification bell so you never miss our latest videos. In the comments below, let us know what calculus topics you'd like us to cover next. Are you interested in integration techniques, more advanced derivatives, or perhaps applications in physics and engineering? Your feedback helps us create the content you need most. Remember, mathematics is a journey of discovery. The derivative of e to the x being equal to itself is just one of many beautiful relationships waiting to be explored. Keep practicing, stay curious, and we'll see you in the next video.